All right. Today we have a speaker coming in to talk to us not just about some technology, some neat technology he's developed, but also his company, which is a not-for-profit, which is unique for an engineering firm. I don't want to steal all your thunder, but this is Michael. He runs HabitatMap, and he's going to talk to you about his cool stuff and how he's changing the way we see air.
Yep. So as Dave said, my name is Michael Heimbinder, and I'm the founder and executive director of a Brooklyn-based environmental health justice nonprofit called HabitatMap. And the primary thing we do is we work with schools and community-based organizations to create planning and advocacy maps. And let me go in a little bit about what that looks like. So this is a poster we made up, kind of visualize some of the projects that we create when we partner with schools and community-based organizations. So the platform, HabitatMap.org, you can put a marker on a map and it's a wiki map, like Wikipedia. So anybody else can come in there and add text, photos, and videos to it, and you slowly create a community-based map focused on different things that have an impact on health and quality of life. So people have made maps about bicycle infrastructure, or solar panels, or contaminated properties, or contaminated plumes, all sorts of different things. And then about 3 years ago now, we launched an additional community mapping platform. But instead of being qualitative information, text, photos, and videos, it's quantitative information. So it's sensor data collected by sensor packages that are connected to a smartphone app over Bluetooth, and it's called AirCasting. This will give you some idea of the architecture of the system. So in the center of everything is the AirCasting app. So it's a free app available through Android, through the Play Store. And then we create our own instruments. This is the AirCasting Air Monitor, and we published a DIY guide, so you can go to our website and download the guide and build your own. It measures carbon dioxide and nitrogen dioxide. And then you can create your own DIY sense device. So we have an application programming interface that's very easy to basically take an Arduino or another low-cost microcontroller and program it to send the data over serial to the app, where it's ingested and then mapped and graphed in real time. We also have commercial devices. So Zephyr is a company that makes physiological monitors. The most popular one is a chest strap that measures heart rate. So if you're a jogger, you can make sure you're getting a good workout. So they have software development kits. So we were able to use that to pull that data and ingest it too. And then we've got luminescent accessories. So not only can you push data into the app, but then you can actually trigger a real-world action. In this case, we're visualizing the intensity of the sensor measurement. So when you're looking at it on your phone and you get, say you're measuring sound levels. When it's quiet, it's green, a little louder, yellow, orange, red. And so then you can hook it up to a luminescent accessory, like a hat or a vest, and then you can see that also, so you don't have to look at your phone and know what the measurement is. And then you can send the data to aircasting.org, where we visualize it. You can filter it by time and date and carrier, or you can send it to your own server, and then everybody else can contribute the same way. So this is what the app looks like. On the left-hand side is a sensors dashboard, which shows you all of your sensor streams coming in at once. So here we're doing carbon dioxide, particulate matter, which are air quality issues, heart rate, activity level. You've got a graph view. You've got a map view. So every second, a dot is put down on the map. It's kind of a little breadcrumb trail that follows where you're going. It corresponds to the intensity of the measurement. And then everything gets averaged together on the crowd map. So each of these measurements gets put together, and then each of these squares represents the average measurement. So you can all contribute data and then see what are the hot spots for whatever parameter you're measuring, whether it be sound or air quality or heart rate. And so this is a session that I took with, I'm going to talk a little bit about this instrument. It's called the AirBeam, and it measures fine particulate matter. And that's one of the things that the EPA measures, Environmental Protection Agency measures all across the United States. It's tiny particles that get deep into our lungs. They don't get stopped by our tongue or our throat or nose hairs. Get deep into our lungs, embed themselves there, or in some cases even pass through into our bloodstream. So it could be something like black carbon from diesel exhaust would be a good example of some of the stuff that you see in New York City. But so this is me. I live in Park Slope, and this is Brooklyn, going over the Manhattan Bridge into Queens. You'll see I got a spike here. You see those orange dots, and you can see it here on the graph. And that's me going over and getting stuck behind a kind of dirty diesel truck. And then the really big spike right here is me going over, ooh, I didn't even know I could do that, fancy. And I see as I'm exiting the Manhattan Bridge, I've got all the traffic backed up trying to get on and off the bridge and the FDR drive. So we're getting really good results from this instrument, and that's been one of the challenges. This is the crowd map again. This is showing sound levels. So every phone has a microphone. So if you download the AirCasting app now, you can take sound level measurements and do noise pollution. Park's quieter, represented by the green. My neighborhood's a little noisier with the yellow. And then down here is an industrial corridor, and you see some of these orange spikes. So this is the AirCasting family. So there's a whole range of different devices that I talked about a little bit earlier that connect into the platform. I just want to go through a couple of them. So this was a neat device that was put together by somebody at Microsoft who works on Gadgeteer, and Gadgeteer is a kind of comparable thing to Arduino. It's Microsoft's version of Arduino. And he made an enclosure that he cut on a laser cutter machine, and then he made modifications using Gadgeteer instead of Arduino, which is what we've primarily been using. And then he put an MQ3 alcohol sensor, and then he's got a little spot here where we can put another one. So just an example of like kind of neat projects that people did independently from us and connected into the platform. This was called the AirGo, and it was put together by researchers at Carnegie Mellon's Create Lab that does a lot of kind of interaction design, electronics, measures CO, particles, temperature, and humidity. But one of the things that we've been really struggling with is if we're going to give an instrument to people and we're going to tell them to take air quality measurements, they're going to be concerned about their health, as you can imagine. So if you see a really high measurement, you're going to be thinking, oh, what's going on? Maybe you'll call the EPA, your state agency, and say, I've got a hot spot in my neighborhood, and then it's a headache for them because they're saying, well, what instrument are you using? What the hell are you doing? So there's a big concern about providing public health information to the public, and it needing to be accurate. And so this was some measurements that we did that basically showed very good correlation between the CO sensor we were using and a calibration device. And this was our original monitor. So the one that was put together by Carnegie Mellon had an expensive sensor in it, $90. It's called electrochemical sensor. And then this one that we originally built had a very cheap sensor that was $16 versus $90, and it performed really, really poorly, we found out. So one of the interesting things that I kind of want to emphasize in this talk is that this was essentially what we're trying to do is measure air quality. And we want to do it because we know certain communities face an inequitable share of the city's noxious infrastructure. So, for instance, if you look at Greenpoint and Williamsburg and Brooklyn and Long Island City and Maspeth and Queens, which, it's around 400,000 people live there, and they have the city's largest sewage treatment plant. 40% of all the waste that moves through the transfer station in the city goes through these neighborhoods. It's got petroleum storage and distribution facilities, so not every neighborhood has those kind of air quality problems. And so we wanted to be able to arm people with air quality monitors. They could take measurements, and then they could basically enact policy change and behavior change. Maybe move from truck-based export of waste to putting out of the barge, because the barge can carry 28 tractor trailers with the garbage. Or maybe you take a different route when you're walking from school or to work, things like that. And it always, so we start off trying to measure air quality, and we know we need to create an instrument. And we needed to create an instrument because one wasn't commercially available. You could go buy a carbon monoxide alarm, but that's not going to be appropriate for ambient monitoring. It's going to go off at very high concentrations. It's not going to go back down. It doesn't respond quickly. So we had to do all sorts of things besides do electronics, but electronics were kind of the core of what we needed to create, right? We needed to create a product. And so here we set up a little calibration lab. So we can send air into here, zero air and carbon monoxide or nitrogen dioxide, send it into a little chamber that we fixed up, and then we can mix the gases at different concentrations and see what the response is. And so you can see this is the red line. This is the expensive sensor. It's responding every time we change the concentration, which is marked by these gray lines. And then these are the original sensors we were using. Go up very slowly, and then when we drop the concentration, they just stay there, right? So we were like, oops. We just created a do-it-yourself guide. We told people how to build this original monitor, and it takes really bad readings. Some of the things we run into, right? So we're dealing with electronics, and in this case, we're dealing with sensors that are not well characterized. The manufacturers who sell them to you will give you a data sheet, but that data sheet doesn't represent how it actually behaves in the field. So some of the things are detection limits. It can't detect really low concentrations. Response time. You might be 3 blocks away, and finally you're getting the measurement that you had, 3 blocks ago. So all sorts of things can impact the type of measurements you're getting. And it's really important that when you put together the electronics, actually, that they take into account some of the complications that can come from working with some of these sensors. So for instance, the electrochemical sensor, the voltages that are there's a resistance, and that resistance changes the voltage, and it's so tiny that if you don't do the electronics properly, then there's all sorts of interference, and instead of measuring the signal, you're just measuring the noise from the electronics. This another sensor that was put together by folks at University of Colorado Boulder called the MPOD. And what they're doing is very interesting in that they'll take their sensors and they'll co-locate them. So put them right next to the state-run monitoring stations. And those are $20,000, $30,000, $40,000 worth of instruments. Expensive stuff run by scientists, and they'll co-locate and then they'll calibrate them against one another. So that's one of the things we're looking to do, and that really is something that will happen on the software side. So talking about improving, this was counting particles, so this is another sensor we use. Another commercially available sensor that counts particles. And then this is just results again showing that as we went along here and made different instruments, we were testing the sensors versus each other, and we found out that we finally found one that worked relatively well. And so this is it. So Dave helped with this. This is called the Air Beam, and I'm going to pass it around. I'm just going to open it up so you guys can see the interior. So this is the current version. This is what we're going to produce and put on Kickstarter. And you'll see it's a printed circuit board and a particle sensor on top, and then a temperature and humidity sensor, which is this white one. And it's all nice and neat. It fits together real nice. And this was our V2 prototype. You can see it's glued together. There's like 7 different components. It took 14 hours to print the enclosure, and to wire up all the electronics took several hours, and then just to fit it into the case and glue it in took another hour. So I'll pass it around just so you can see the contrast between our V2 and our V3 prototype. And our V1 prototype was so ugly, I didn't even bring it today. It was a box. It was very badly designed. And the interesting thing about this too is that, so we were able to successfully put together the electronics. The problem was that the sensor works by pulling air through a sensing chamber. And so as it pulls air through a sensing chamber, there's an LED light, and particles come in and reflect, the light gets reflected off it to a detector. And so what happens is that you can imagine you can go outside, and what's pulling air through is a resistor. And it's basically just being used as a heating element. And so it heats up, and then it creates a convection current through the device. So 2 things happen. One, it's orientation specific. So if I'm heating the air here, this is what I want. I want to heat the air here, and then it kind of pulls through the device, right? So all of a sudden, if I lay it outside, it's heating it, and there's no convection. Or if I go outside and it's really cold, it's cauterized. Or if it's really windy. And so one of the important things when you look at the enclosure, you'll see that we made a big effort to make sure that this fan can connect and pull air through the instrument. And in addition, we had to make sure there was no stray light, right? So if we're looking at light scattering, and then we get sunlight in there, we think we're seeing light scatter when in fact we're just getting light intrusion. So again, we knew we needed to nail the electronics, but in fact, the mechanical component was really important. We needed an enclosure that would maintain a consistent airflow and block light out.